Hello, everyone. So, I'm going to keep this somewhat short stream, I hope. I may blabber on for a while, but I do have some new ideas I want to talk about. So, you'll see I have the paint window up. Also, just on a side note, if you hear my mic disconnect, that's been a problem in previous streams, so please let me know. But at the moment, it looks like it's working, so I'm hoping there's no feedback or anything. I do plan on looking into that in the future to try and get possibly a new cord or just make sure this cord is connected the correct way. So the reason that I have this paint window up is that I want to I want to for you guys to be able to visualize what I'm talking about, because I feel like a lot of this is going to be a little bit abstract in terms of the math, but also mathematics. So it's kind of nice to see what I'm saying. So um, basically, as you know, I have been working on the data mining project, and it was successful once, and I retried that exact same code, and it was not successful again. I tried it a couple times, and it got close, but it never hit the nail on the head, which means that the first time got pretty lucky, especially since it did it in 85 generations when the other ones didn't even get to an answer in 150 or even 300 in one case. Um, and I have since ended those running, which is why you're not seeing them on the screen right now. But I just wanted to kind of go over the new idea I'm having and the reasons why I think this will be an improvement. So currently, there's two ways of mutating with the AI. So with deep learning AI, the deep learning can add in new complex variables that are combinations of other previously used variables, or the AI itself can mutate the structure of the variables. Now, I think that this may be that may be a little redundant. So what I'm going to do is bring back uh, so tailor back the mutation of the actual AI. So when the AI runs through and mutates, it won't have as much freedom in what it's mutating. So essentially, what's going to happen is the AI is going to pick a linear combination of the available variables, and then, as you will see with the title of this stream, through an iterative process called Gauss-Seidel iteration, or a more theoretically better version would be Newton-Raphson. But in this case, I believe I'm going to be using Gauss-Seidel. I can explain that in a second. But this iteration allows so basically, if there's a linear combination, which if you don't know what a linear combination is, essentially it's A plus B plus C, and these can be anything. So this could be some chunk of an equation that's being added to some chunk of an equation that's being added to some chunk of an equation, because the the deep learning will create what is possibly being plugged into these spots. The AI will decide how many it wants and where they go. Um, so, because addition and subtraction are pretty, they can switch places. There's no real big problems with order of operation. I think this is a pretty strong way to do it, just because there isn't the chance that the correct thing is there just in the wrong order, so that it doesn't work out. And what I'm going to do is tack on coefficients. And so there will be these coefficients here. And this isn't the best notation for writing out a linear combination, but essentially what I'm saying is these big letters, the capital letters, are something that it's a variable that is either an original input variable or was created by the deep learning. And then these coefficients are going to be used in order to find the least squared regression, so that this linear combination is optimized for the minimal least squared possible, or at least as good as I can get it with this iterative process and with the tolerances I set. So first off, I'm just going to write out the Newton-Raphson equation. So Newton-Raphson is essentially what an iterative process is it's the way that computers approximate things that we would normally solve out. So if you have a system of equations, obviously you can solve out that system of equations assuming that you have the correct number of equations for variables. But if you give this system to a computer, there are some clever computer programs that can symbolically solve these equations. But most of the time, simply for speed purposes, computers will solve out the system of equations with an iterative process. So Newton-Raphson is one of the fastest iterative processes. I'm not going to get into the specifics right now. If this is something that interests you while you're watching this, please let me know, and I will make sure to go into further detail in a later video, probably on a Saturday video, just because that's when I usually have my detailed topics that aren't about the AI. So Newton-Raphson. So we have Newton-Raphson labeled NR, Newton being, I believe, Isaac Newton, and Raphson being another person. But then what Newton-Raphson does is it takes a all right, let's look at an equation. All right, so we want to find the zero of an equation. So we are setting f of x equal to 0, right? So if f of x is x plus y plus z, then we want to find okay, let's make this a little simpler actually. Let's just say f of x is x plus 2. We want to find which x can be plugged into here to make this a true statement. So the simple algebra way of doing this is moving the x over to the other side. So x in this case would equal to -2. But let's say this -2 isn't just a coefficient. Let's say this is some g of x. So what this would do is when we plug this over here, now this is an exact statement, but what an iterative process does is it takes a guess, plugs the guess into this equation, and gets a new guess. So this would be xi plus 1 is equal to g of xi. And the way this works is if this equation, if this g of x is adjusting is converging towards the answer. So there's some criteria, and like I said, if you want me to go into more detail with that, I can in a later stream. But Newton-Raphson is a form of this equation. So Newton-Raphson is xi plus 1 is equal to xi, so this is the old x, plus your f of x you're working with over f prime of x. So this is the derivative of f prime of x. If you don't know what a derivative is, you can go check out my video on calculus. I give a pretty brief description, but I think it's thorough. So this is Newton-Raphson, and the reason that this works very well is because it actually converges quadratically, which, as opposed to linearly, is significant. So this is a lot of terminology in the terms of iterative processes, and I encourage you, if you are interested in this, do some research on your own, because this is a very important idea in computer programming and in general with how we handle things with science today. So what Gauss-Seidel is, which is what I'm planning to use, is a variation of Newton-Raphson that removes the necessity of doing derivatives. So what Gauss-Seidel is that it's essentially an approximation of the derivative. So, but what I'm actually doing is so I'm approximating this derivative with f of f prime of x is equal to, and I'm using the central difference, central finite difference. So what this means is I'm using f of x plus some epsilon um, minus, or yeah, so f of x plus some epsilon minus f of x minus some epsilon all over 2 times epsilon. And so what this does is this is essentially your slope formula. So if you have m equals f of x1 minus f of x2 over x1 minus x2, then you get the slope. So that's essentially what the derivative is at that instant. The reason that this is an approximation is because these slight adjustments aren't technically exact. So by doing this, you're approximating it by, so what's happening is if you have a line like this and you're trying to find the slope here, you're essentially taking a step this direction, taking a step in this direction, and drawing a straight line, which is usually a pretty good estimate, especially on a very small scale. So that's the reason that this epsilon is here, because this is something on the order of I might have drawn that. No, I don't think that epsilon's backwards. This is something on the scale of, like, I think what I'm going to use is 10 to the negative 7. That's kind of an arbitrary mark, but it's relatively standard to use something around this number, or maybe 10 to the negative 9. It depends on the computer you're working with and whether you're working in floats or in just regular integers. But so Newton-Raphson is a very fast process, and like I said, I can explain it a little bit more if you want me to. But what I'm using this for is actually to solve the system of equations in a sense. So I'm going to clear the slate a little bit and just show you what's happening. So once again, we have our A plus BB plus CC. And so what's going on is we know what these are. The data, the deep learning has given us these variables, and the AI has told the program to use these specific variables in this order. So then the least squared regression, or Newton-Raphson, is going to figure out what these variables are, simply because in this process we know the answer. So we're trying to approximate some z, right? And essentially what's happening is we're setting up an equation which is equal to 0, just like we did in the previous state part. So what we're doing is we're saying that all of this function, so I'm going to call this big F of x. So we're saying big F of x minus z all squared, which is why it's least squared regression, is equal to 0. This is essentially what we're trying to achieve, because if it's equal to 0, that means the equation that we've brought up is equal to the equation that we used, that was actually used, or is equal to the model. It's a very good model in a sense. So we're trying to make this least squared. It's called the least squared because we're trying to make it as small as possible. So what I have to do for this is essentially do Newton-Raphson for each individual variable here. So since this is our equation, right, what we're doing is we're taking we have to create three equations, and so this is a part that I'm been a little iffy on whether or not I'm doing this correctly. But please let me know if you see any problems with this. What I'm essentially planning to do is have the first variable update, so that will be ai plus 1 is equal to ai, and this will be minus our function, which this is going to be we'll call this one g of x. So g of x is our least squared regression. And so we have g of x, and this is going to be over our approximated g prime of x. So this will be approximated simply by slightly adjusting the a term. So this prime is actually it's actually going to be g. It's going to be dg of x with respect to a. So I mean, calling it g of x is probably a little wrong. So this is just some function, and then this will be g, which is the function here. So that's what we're working with. So it's the derivative of g with respect to a is the bottom of this fraction. And then what we would do after that is now we have a new a, so we're going to plug that in to the next equation, which is bi plus 1 equals bi minus g over dg with respect to b, because now we're talking about b. And so the reason that I was worried about this was because if you have the exact same equation that's just been rearranged, then it doesn't work for solving equations. But the reason that this should work is because of this term being different, and these terms are also different as well. So I'm pretty sure that I'm correct in how I'm doing this. And then, of course, we'd have the same for c, so this will be the same thing. And so what this does is it updates the first variable, and then this variable is technically more correct. So it uses that to update the next variable, and now it has two more correct variables, and it uses those to update the last variable. Now this can go on for as many dimensions as you want. So all you have to do is make sure to adjust the equation for the specific coefficient that you're using. So this is why this is nice for the setup that I'm planning to use, because this linear this addition of the individual pieces could be infinite. Now, obviously, there's going to be limitations on how many variables can be added on a specific level, just so that there isn't that infinite length. This has been a problem I was having with the previous one, where it would become extremely complex for no reason. So that's basically the idea, and so I need to sit down and actually work through the code of that. I have tomorrow off. I have a little bit of homework, but I'm planning to do some work on this, and but that's the general idea of how I think this will improve the AI, because what's going to happen is every step of the way, the equation that has been created will be optimized to be as well fit to the data as possible. So even the first bad equation, which will just probably be some number, will be fit in order to be a best linear fit of the data. And so this least squared is actually, it's the sum of all the least squared. So it's the sum of all the squares. So this function is going to be tested for all of the data points Probably. So what I'm thinking, since I am planning on having databases with large amounts of data, is that a sample will be taken, um, and so I'm thinking that that sample should be different each time in order to ensure that all of the data is being represented. I'm not sure if that's a smart idea because it might. So I think what will need to happen is each least squared regression will have to have a constant set of data. But when I move on to the next equation and begin to evaluate that, I will get a new set of data that has been randomly selected. And then what I'm thinking is that I will keep the parameter that I recently put in one of the later versions of the data mining project that retests the possible best programs to make sure that they didn't just get lucky. Now, this is important because if, let's say, there's 10,000 data points and I take a sample of 100, it's possible that those 100 are just extremely luckily right on the line that the AI has created. Um, and then it gets a perfect score. Well, if it goes and then I retest it with 1,000 data points, the probability of that happening again is very low. So, unless it is actually a correct equation. So, this is what I'm planning to do. And I'm hoping that this will speed up the process because each individual equation will be optimized. Now, that optimization takes some time, but Newton-Raphson in itself is very fast. So, assuming that I do my job correctly on the coding side, this should speed up the process, if and hopefully um, also improve the probability of success. So that's pretty much what I wanted to talk about on my new ideas. I don't know if there's any questions in the chat. I know that I'm running on around 22 minutes now, which is a little longer than I was expecting, but then again, I have new ideas I wanted to explain, so I can only assume that I'll babble on for a long time. It does look like the mic has been successfully picking up my voice this entire time. Um, so I'm not seeing any questions in the chat, but I want to thank you guys for watching. A big note is that on Saturday I have something I'm doing, so I will be streaming on Sunday night. That time may vary a little bit, just because I usually watch football, and but there's a nice break right around I believe right around 8. So let's just shoot for 8, and then I'll post on the Facebook page if anything's changing. But other than that, I want to thank you guys for watching, and I will see you on Sunday.